You are forgiven. Right? All right, so that's all right. You're not late. You're fine. So if anybody has a particular question, let me know now before I do. Can I do part A of number 1? Which homework, Becca? 3 or 4?
What homework? Is there a homework due tonight? Is it homework 3?
Homework 3 is probably due tonight, but you can turn it in later if you want. Let's see. Yeah, homework 3 is due tonight. Okay. Technically, the official due date. Okay, so let's make note of this. That when I want this guy is due Tuesday. So whatever date that is, 9/22, and then this creature is due tonight, officially. And look, when I say officially, don't forget the point of this. Due dates are not there to punish you. Due dates are there to remind you that if you're still working on it after that date, you're behind. That's the point of a due date. I will still accept homework after that. Now, if you submit it 3 weeks from now, you might lose points, right? But you submit it a day or two late, I'm not going to be mad. Typically, my rule of thumb is that I don't mark it late until I've graded them. And I'm not, I usually, you know, I usually wait a day. See, here's the thing. My grading depends on, what's that?
You said you grade them all at the end.
Nah, how terrible that would be. That would be good for some of you, right? No, so typically, you know, sometimes I wait to grade an assignment. Like if it's an assignment where we've done 90% of the problems together, there's no rush for me to grade it, right? Because anything that you've done wrong on it, hopefully you can fix. And everything you've done right on it, I just assume you got it right because you knew it. Actually, I assume you just copied it off the class board. Right? So anyhow, let's do, Becca said she wants to do 1A, I think. Is that what you said? I think. And that's what we'll do. So this is a good problem. So for fun, Becca, we're going to do a slightly different version of it, though, because why steal all your fun? We're going to do this one. So, but this is very similar to homework number 4, 1A on homework 4. So just so it's not so much boringness for you guys, I'm going to do it this way. Instead of doing x squared plus 4, I will shock the world and do x squared plus 25. How's that sound? So you only have to make minor modifications if you'd like to copy down the answer. But hopefully you'll take the time to learn and check your answers correct. Okay, so look, I don't want to write down all this trig stuff again because we're limited on time. But here we go. So what does the x squared plus 25 scream to me? Now, let me say a couple things. One thing that needs to be understood, and if you notice on these homeworks, I'm telling you, you should be reading chapters 8, sections 1 through 7. I can't emphasize how important it is to look at the examples and read the sections and understand that in general, when you're given an integral, there might be multiple ways of doing it. And one of them might be easy and efficient. The other might be extremely difficult. They might both be difficult. There might be no ways of doing an integral. So when I first look at this integral, the thing that screams to me is the square root term. So let me explain what I mean. So if I want to do this solution, here's what I'm going to note. The x squared plus 25 screams to me x equals something. It's going to equal 5. Now, what do I want it to equal? I need to remember which trig identity is the one that applies for this. So I have a couple, and you know, you say to yourself, okay, do I use sine or do I use cosine? You know, do I use secant? Do I use tangent? And really, you only have a finite number of choices. So in the big scheme of things, you can try and fail one or two of them before you get sort of the right, I don't know, I want to say right way of doing it, but before you get sort of something that's useful. Now, I will say this. It doesn't hurt when you're doing this homework to have somewhere next to you have these things written down, like something like 1 minus sine squared theta equals cosine squared. That's one that's useful to use. And then you also have the tangent squared theta plus 1 equals secant squared. And then, of course, if you rewrite this, you can also say that the secant squared, well, I shouldn't write, why did I write x's here? That's a typo. These are not x's. I got 2 letters written around. What a knucklehead. Fire me immediately. And if you rewrite the second one, another thing that comes into play is that secant squared minus 1 is tangent squared. Although I guess technically I've written that incorrectly. Oh no, that's fine. So the purpose of writing these down is that you look at these 3 identities, and the left-hand side of them is a something minus a square equals a square, or something squared plus 1, something squared minus 1. So the fact that my guy is x squared plus 25, this screams to me to set x equal to 5 times the tangent of theta. And if I do that correctly, that means that dx is 5 secant squared of theta, d theta. And so my original integral then becomes x squared downstairs. Inside I have x squared plus 25. And I have a 1 here. Now what does this equal? This equals the integral. So downstairs I get a 25 tangent squared theta. Inside I get 25 tangent squared theta plus 25. And then my dx becomes, I'm going to write the secant squared up top. And then I have a 5 in front of it. And then I have a d theta. So that's what happens when I perform my trigonometric substitution. So at this point, whenever you're doing it, it's very important, I think, that you go back through sort of what we did or what you did specifically and ask yourself, does it make sense? Yes.
Can you do secant in the denominator and do tangent in the numerator? Or is that completely different?
I'm confused what you're talking about.
Like you chose tangent for the bottom,
I chose tangent for x.
so you can choose whatever you wanted.
Well, right, but this is the way it's going to work. If I chose secant, it's not going to work. So the secant's a bad choice here because the identity where secant is useful is secant minus 1. So that's why it's a bad choice. I have something squared plus.
Oh, okay.
If it was minus, it would be secant.
Okay.
And then if it was flipped, if it was 25 minus x squared, I would use x equals sine.
Okay. Oh, that makes sense.
Okay, so this is, and I hasten, that's such a terrible word, but it's applicable here. I hasten to encourage you to like memorize those kind of things. I would rather you think about it each time, because when you think about it, it's going to take longer for you to get it correct, but then you're more likely to retain it. If you just start memorizing which identity to use and when, I think that sort of hampers what you retain. Okay, so lots of stuff happens here. First off, I can pull my 1/5 out. And then why do I get 1/5? Because I have a 5 over 25. And so I'm just going to go carefully here. Upstairs, I'm still going to have secant squared. Downstairs, I have a tangent squared. But inside I have the square root of 25 tangent squared plus 25. This is the same thing as 25 secant squared in the square root. So you'll notice I'm going very slow here. And before we go to the next page, we can simplify this a bit further. I can pull the square root of 25 becomes 1/5, so I now have 1 over 25. I have a secant squared in the numerator, and I have a secant in the denominator, so this just reduces to secant theta over tangent squared, theta d theta. So if you have a question, a comment, again, these are difficult integrals. They are time consuming. There's plenty of places to make errors. There's lots of places where you get confused and second guess and triple guess. Say, oh my God, did I do this right? And then you have imposter syndrome. Maybe you're not smart enough for this, which is a bad thing to have, but don't roll your eyes. We all have it. Everybody has it. Okay, so here's the thing. You don't have to do this, but the O'Grady sort of way of thinking, listen to me, what an ass, I'm like talking in a third person. The O'Grady way is I hate writing things in terms of secants and tangents. I would prefer everything's in sines and cosines if possible, because that's just more familiar to me. So what I'm going to do is I'm going to remember that secant is 1 over cosine, and I'm going to remember that tangent is sine over cosine. So if I go to the next page, this becomes 1/25. The integral, so secant is 1 over cosine, and then tangent squared is sine squared over cosine squared. So let me make my integral sign bigger so it's not such a... Here, let's adapt and plan ahead. So this is 1/25, this integral. Now this integral is, this looks like a mess, but when I was in 5th grade, I had this teacher named Mrs. Cooper, and she was a badass math teacher. And she taught us that if you have a fraction divided by another fraction, Miss Cooper said, you take the denominator, invert the damn thing, and multiply. And we said, all right, Mrs. Cooper. And we listened to her. And then literally for the next 3 days, we just did that 1,000 times a day. And then we'll never forget it. There you go. And so Miss Cooper taught me that 1 over cosine divided by sine squared over cosine squared would be 1 over cosine times cosine squared over sine squared d theta. And of course, this simplifies now to 1 over, excuse me, not 1 over, simplifies to the cosine divided by the sine squared. Now, here's where it gets very demoralizing when you're doing these things, is we put all this work in. We feel like we split an atom. We feel like we got a rocket to Mars. And we ain't even close to done because this thing looks like bad, right? Problem, it looked, well, it's beauty's in the eye of the beholder. It looks good to me. I'm ready to marry this damn thing. Can you marry integrals? That is the question, because this will be a good one. Because it looks scary, but it's so damn bloody easy, as the British would say. Is that a cuss word in Britain? Like if you say bloody in public, do you get in trouble? I don't know. These are questions I have. Yes or no?
They say it in Harry Potter, so.
Oh, well, I don't know. I've never seen Harry Potter. See, can you imagine her? I swear to God, well, I'm too old. I'm too old for that.
Next Friday's movie.
I bet you, what's next Friday?
We're watching a movie.
In here.
Yeah.
Isn't there like 10 of them? I got a problem. You know what else I hate? Not to change the subject. I got a big problem. I got a massive problem with superhero movies. Like I can't, well, but they, do they fly in brooms? Is there magic? It's a, yeah, I ain't got no time for that. No. I draw the line at movies where the action is not realistic. You know, like I'll watch a movie where like The Rock's in it and he'll climb up a helicopter from a building, and I know that's phony, but I can get behind that. I don't want to see superheroes. I don't want to see superheroes. I don't want to see some kid playing a game.
See somebody get turned into stone.
Nah, I don't know. I guess I should check it out. Everybody says it's good, but isn't everybody mad at the author of that now because they said she's mean or something? I saw everybody on the internet getting mad at her because she said something about, I forget exactly what it was. But they were mad at her because they said she was a B, you know, B-I-T-C. You finish it. All right, son of a ship. All right, anyhow. By the way, this, you know, I kid about this integral because this was really a nice one in disguise. This integral requires nothing more than a pretty straightforward substitution now. The substitution is now we introduce a new variable, I'll call it y equals sine. And then, of course, dy equals cosine theta d theta. And so if we go back to our original marker, this integral now is 1/25 1 over y squared dy. Ain't that something? It looked like it was going to be a fiasco, and then that's what we get. And I like to write these things in a little simpler way for my mind, so I'll write this as y to the power -2. And then now I do my integral. I add 1 and divide, so this becomes -1/25 y to the -1, which is times 1 over y. And of course, this is plus c. Now, we ain't done because we went 2 currencies away from where we started. We started in X. We started with the United States dollars. Then we went to theta, which is like the Russian ruble. And then we went to Y, which is like the Japanese yen. Is that what they use in Japan, a yen, or am I correct? I don't know. I'm asking you like you've ever been there. Anybody here been to Japan? I don't know. So we went from X to theta to Y, and now we got to get back. So let's take a pause for station identification. What a hell of an integral, by the way. And Becca, thanks for asking about number 1, because you assumed it was probably the easiest one because it was 1A. But really, this one was brutal. I hope you asked about 1A. I'll be very mad if you didn't. We went through all this. Yeah, no. Wasting my time. No, I'm just kidding. I kid because I love. You guys see me today? Let me see what I look like here. Let me see. Hello? Why ain't you showing me a picture? Where am I? There I am. Ooh, I look like a cretin. Here we are, live and direct from, what room? What is this? The Hewlings Academic Center? HAC?
Yeah.
Good deal. All right, so let's put a little multiplication thing here so the brains get it. So here's what we got to do. We got to get back to our original variable. So let's write that in proper O'Grady grammar. We got to get back to X. I wish this was like 1999 and I can reference like X gonna give it to you, this rapper DMX, which none of you know because that was 20 years ago. Go Google DMX. All right, so how do we get back to X? Well, we're gonna have to do a few things. We're gonna first note that, so let's sort of regroup. So our original integral was 1 over X squared times the square root of X squared plus 25. That's kind of, yeah, that's okay. And what we know is we now know that this is -1 over 25y, correct? Plus c. But now we have to get back from y. So y we know is what? Y was the sine of theta. So we can write this then as -1 over 25 sine of theta plus c. And now we got to somehow recover x from this. So let's remind everybody of what was happening here. In this particular step, we have to recall that y was the sine of theta. That was our substitution. Whew, what a time to be alive. All right, so we need to get back sine of theta. So this is where we draw our little triangle action. So let's draw our triangle. Now, what was our original substitution? We might forget this. So we have to go all the way back to the first page and we say, oh, that's right. X was 5 tangent of theta. So what I need to do is I need to take that relationship, X equals 5 tan of theta, and I need to write it in terms of that triangle. I want to look at it from its geometric point of view. So if I have X equals, here's my theta, If I have x equals 5 tangent, that means x over 5 is the tangent. So tangent is opposite over opposite over adjacent. And so by the beauty of the Pythagorean theorem, we get that this side is x squared, as we should expect it to be, our original thing, x squared plus 25. So then this gives us all we need to know, because all we want is the sine of theta. And so the sine of theta, let's write this out. This is -1 over 25. What's the sine of theta? Well, the sine of theta is x opposite over hypotenuse. And then, of course, the only thing left I would do is clean this up. You have to flip this thing. This would be negative the square root of x squared plus 25 all over 25x plus our arbitrary constant c. And what a friggin' mess. What a mess. But we should be so proud. We think we got it correct. Fun? Showbit? No? Just say yes. If I gave you a quiz right now and said, how much fun on a scale of 1 to 10? You should easily say like 10 times. What's that? Nah. I mean, what better way? Like I said yesterday, one day you're going to be walking down an alley and some mugger is going to come after you and say, give me all your money, or give me your Apple Pay ID or something like that, right? And then you're going to say, no, no, no. And he's going to say, can you integrate partial fractions? Can you integrate trig sub? And you're going to be like, yes, I can. And then he'll say, you're fine. You don't get mugged. Yes.
I'm sure that'll happen.
You never know. It could be me. Give me all your cash. I'll come up. I'll send Samuel L. Jackson. He'll be like, give me all your cash. It'll be fun. What a life that man leads, I should say. Ever think about if you could be anybody in the world, who you would be? He'd be a good one. Any questions about this? This is a brutal problem. I mean, it took us, what, 25 minutes to get to. We didn't go that slow. I mean, woo, that was fun. Yeah, so that's a brutal problem. And look, I don't want to, scare you, but most of the problems on this homework are pretty brutal. But you should accept sort of as a challenge and want to go from there. So again, problem 1, A through F, or excuse me, I guess A through J, those are, some are partial fractions, the other ones are trig subs. It is, this is, I think I told you this last class, this is probably the one of the more difficult homeworks you'll do all semester, particularly in challenge, level of challenge, but also time. If you go through all these problems and you do them correctly, it's going to take a lot of time and effort on your part. Now, of course, you might not want to do that. Yeah, do you have a question?
So for problems like E or F, would you just break up the column in one?
Yeah, right. So that's a good question. So the question was asked, what about number 1, E and F? Well, you have to factor. That's correct. So let me give you some hints on some of these to get you started. So this could be, could it be of use? Yeah, we'll do one back up. Yep. So what we'll do is let's do F. So here's the integral. The integral is 1 over x squared plus 5x plus 6. And the observation to make, if we want to do anything with this, is that the denominator can be factored. How is it factored? It's x plus 2 times x plus 3 dx. So if you look at B, I've already factored B for you, but E you're going to have to factor if you want to do it. So you'll have to learn how to, not learn, but in problems B, E, and I are similar. So, oh boy, I hate when that goes AWOL.
Is J literally the same problem as A?
No, well, J's similar to A, but it's not the same because there's a minus instead of a plus. So you have to use a different identity,
Yeah.
right? So you'll use, what identity you'll use is use x equals a secant. Yep. Okay, so here's what we need to do. In order to do this, we need to decompose. So we need to determine A and B such that 1 over x plus 2 times the quantity x plus 3. We need to know A and B so that this is true. Now, there's a couple ways you can do this, as I alluded to. At least there's a couple correct ways. Some of you will come up with your own ways that are incorrect. There are a few correct ways to do this. And I think that you should just pick one of them. And so I will continue to do it the way I did yesterday. I'm going to deduce without guessing and checking. I'm going to deduce in a logical way. So what I need to recognize is that this line right here is equivalent. And so remember, anytime we use this double arrow, this you can read this as this means equivalent. So this equation right here is equivalent to what I'm going to write on the next page, which is 1 over x plus 2 quantity times the quantity x plus 3. And then what is this going to be equal to? It's going to be A times x plus 3 plus B times the quantity x plus 2 all over the denominator x plus 2 times x plus 3. And this, of course, is going to be equivalent to the following. Now, what I told you guys yesterday was the denominators are immaterial. What's that? Yeah, hold on. Someone wants us to go back. We're going back. Yeah. You got to yell at me sooner. Scream and flag down like you work at the airport. Like those guys, right? You see what I'm talking about? Or women. What's that? I know, I should get you guys bells. This will be good. We'll get you like bells. You ever go like a ding? We'll get you one of them. Yeah. Everybody's shy. You good? All right, good. So if I find a common denominator and add the right-hand side together, I get this creature. Now, what I'm saying is since the denominators are the same here, I can ignore them, but I'm not really ignoring them. I can multiply both sides by them and they go away. And so what this is equivalent to is it's equivalent to this. It's equivalent to AX plus 3A plus BX plus 2B. And this is equivalent. What I want to do is I want to write the right-hand side out. So I'm going to group my terms. I'm going to write 3A plus 2B in parentheses. And then I'm going to factor out an x. So I'm going to write A plus B times x. So what I've done is I have the number 1 on the left-hand side. And I want to match my coefficients. On the right-hand side, I have a polynomial. I have some number plus some number times x. And I don't know what that number is yet because I don't know what A and B are. But I can deduce that. So what this leads to is something that you did in an algebra class called a system of equations. So this is true provided 3A plus 2B equals 1 and A plus B has to be 0, just like we saw yesterday. The only way this thing works is if those numbers A and B satisfy those two equations. So if you have a question about that or you're curious what I mean, please ask. And let me also reiterate, for this line right here, let me put a star here. So for this particular line to be true, I need this has to be 1 and this has to be 0. That's the only way that that starred line makes sense. It's the only way. At least that it makes sense for all values of x. Maybe if I'm being more specific. Now, what does this thing tell me? Well, there's a couple ways I can solve this. Maybe you remember how to solve them, but this one's pretty quick because the bottom equation tells me that A has to be minus B, right? So this tells me A equals negative B. And then if I plug that into the top equation, that tells me that negative 3B plus 2B equals 1. And that tells me, of course, that B must equal negative 1. Because I'd have negative B equals 1, which means B has to be negative 1. Now, I have reasoned this in a logical way. You can't argue with that reasoning. So if B is minus 1, then what this implies is that A is positive 1. So maybe we can just all sort of follow this line of reasoning here. We'll delete this little creature. Look at that, a nice little train of logic. Choo, choo. And then I wish it was, if I was Samuel L. Jackson, I'd say choo, choo. But I ain't. We can hire one of you to be our censor, since this is an all ages affair. No, it's not. This is a college course. You're 18. No, I'm just kidding. Okay, so does anybody have a question about this? Okay, so good. So what do I know then? So I can conclude the following. That the original integral, which was x squared plus 5x plus 6 in the denominator, is by factoring this integral and then of course this is, as we saw, is just 1 over x plus 2 minus the integral 1 over x plus 3. And what you should do is you should absolutely verify this for yourself, that does work. You shouldn't just assume your algebra above worked. Turns out this does work, so we're excited. And then these are two basic integrals that don't even require much more than understanding the basic rules, that this is log of x plus 2 in absolute value minus the natural log of the absolute value of x plus 3. And then, of course, your arbitrary constant. And that's it. All that. Woo! Woo! Fun is in the eye of the beholder. 'Tis it not. All right, any comments about this? Becca, does that make sense, hopefully? Again, these things are brutal. They require, I hate to, one of the things you do need to get in your head when you're in a calculus course, particularly something like this course, is more often than not, you're going to get things wrong before you get them right. And you're often going to get things wrong a few times before you get it right. That's mathematics. I mean, problem solving in general is not an instant sort of thing. You can't expect instant gratification. It's a tedious affair. All right. With that in mind, I guess we got to call it a day because it's time for the class to end. What, 12:35, right? So even though you arrived fashionably late and later, I kid, of course. I kid. You know I'm joking. You know I'm joking. It's tough for me too. Anyhow, listen, guys, thank you very much. Have a good weekend. If you have questions, please email me. And I will see you guys Tuesday. So be safe. Thank you very much.